Okay, so now I've done. Please don't ever don't think that this is not important or a waste of time. It is not, my friends. Let's go. This is an important journey which will help you. You know, if you want to study engineering, you're going to meet this. If you want to study whatever, especially in engineering, you'll meet this a lot more. You're going to be integrating and differentiating a lot more. Now, these fundamentals that you're getting right now, okay, you're going to get more in this, but these fundamentals you are getting right now will be so vital. You'll see it. It's going to be so important. I want you to make sure that you stick everything to your heart. I'm giving you something which I know you're going to be able to do well with. Now, there's one more thing I want to tell you before I show you this thing. And I want to teach you the idea of composites. Now, it is going to make much more sense or more important thing when you are doing differentiation. So, here is the thing. Everybody, even for integration, it will work. Everybody has seen what the function is. You have all seen what the logarithmic function is. It is only y equal to ln x, or f(x) equal to ln x. It's the ln x. That's the logarithmic. The inverse trig is tan inverse of x. The algebraic is x squared plus 5x minus 9 or stuff like that. The trig is sin x or cos x or tan x. The exponential is e to the x. These are the ones. So now, what happens when, because first of all, you have to know how to differentiate each one of this. And we teach you, right? And we're going to give you this. And all of them you are taught in one table. And that table is called the common derivatives table. They teach you how to differentiate this. Now, you also got to know how to integrate some, or how to integrate something to give you this. So either we are going to integrate like e to the x, we can integrate him. But for tan inverse, we won't integrate him, but we will integrate something that will give you tan inverse of x, because you would have learned how to differentiate it. You differentiate tan inverse to get something, and you can integrate that something to go back to tan inverse of x. So you're going to be learning how to integrate things that give you tan inverse of x, and you're going to learn how to differentiate tan inverse of x. So you need to know. You see, when you look at all these functions, you gotta know, okay, this is your P3, people. This is your P3. It's the differentiation and the integration of these guys. So first you got to know how to differentiate each one of them, how to differentiate ln x, and how to integrate something that will then go back to give you ln x. Okay, we won't integrate ln x himself. We can do it in parts, but you are going to be usually getting things that you integrate to go and give you ln x. We'll see what you do if you ever get an integral of ln x though, by the way. No, so I want you to master. Okay, so sir, are you telling me I'm going to get to differentiate all of them? Yes, you should know how to differentiate all of them. But then you are not yet done, because when you know how to differentiate all of them, the next thing they would want you to know is how you differentiate things when we combine these functions. And that is when you start getting those rules: product rule, quotient rule, chain rule, and then you're going to meet them again in integration now. So we don't have product rule in integration. We are going to have integration by parts, integration by partial fractions, integration by u sub. That is the equivalent of differentiation by quotient rule, product rule. You see what I mean? So first of all, so this is how your differentiation will be like. Now look, maths is easy. Maths is a walk in the park. Okay, I actually made a video somewhere and posted where I explained things to do with this. But here I'm doing it. You know, it's always whenever you do something and you speak from the heart or something, yes, you can trust yourself, because in here I'm just using another way, probably different from the way I said it, similar to things. I mean, I'm teaching you the same concepts either way. So in differentiation now, when I now take, okay, because you are going to say, sir, you are telling me that when first of all, I need to know how to differentiate this whole table. Yes. And you said it is called the common derivatives table. So I need to be familiar with the common derivatives table. Yes. And some part of it you just look in MF19, but you must be so good, because there are some versions that we are not going to take directly from MF19. We're going to need to know. So you need to be able to know your common derivatives table by heart. Yes. Okay, so common derivatives table, yes. Mostly the things you're going to some things you're going to get from the MF19, yes. The booklet, yes, which we have in the exam, yes. But some no, yes. And so you're going to write on your MF19 and edit it a bit, yes. So we'll talk about it. So common derivatives table will tell us the derivatives of all these guys, and you can actually use it to know integrals that give you those other things. Fine. So common derivatives table, we can talk about the common integrals table, but you can use the common derivatives table again for integration because you'll be just going in reverse. But yes, we can say common integrals table is just a table which then shows you things that you integrate to go back to each one of this. So I need to know, what do I get when I differentiate ln x? What do I get when I differentiate tan inverse? That's what I'm saying. And also the sixth trig, you need to know what you get when you differentiate. You have to. Now let's say you now know. You say, okay, so where do these other things like product rule come in? What is that? Because I want to give you the whole picture of, you see, product rule will come in when you are now combining. Because what will happen is, first you are differentiating them individually. Now when we are sure that you know how to differentiate them individually, we'll start mixing them. And we'll ask you to differentiate. We'll say, please differentiate for us x squared sine x. Woo! What is x squared? It is an algebraic thing because it's just x with a power. What is sine x? It is a trig. And what are they doing? They are multiplying. So you are differentiating two functions? Yes. That's why I taught you the functions. I made sure you know them. You see, now you are differentiating them whilst they are multiplying each other. That is where you're going to use the product rule. That is why you learn about it. And then you say, oh, what about the quotient rule? Because I've also seen something that talks about the quotient rule. Yes, I say, yep. So when am I going to use it? When you have them dividing. Any two on the list, come on. If I give you, say, let's say cos x over ln x. They are dividing. And I say integrate this. You would have known how to integrate cos x first. You'd like how to integrate him. And you would have known how to integrate anything, let's say, that has an ln x. Or let's say cos x over, let me make it easier and nicer, cos x over e to the x. You would have known how to integrate e to the x. Now you have them dividing, so the only way to integrate when they're now dividing is to then use the quotient rule. Because you are combining two things and they are dividing two functions. What about the chain rule now, which is a very important thing? Oh, here we were talking about differentiation, by the way. So yes, it's cos x over ln x, and we can ask you to differentiate this. And you have to use, it's not integration. I'm sorry. I'm so sorry. That was wrong. For integration, we don't use the quotient rule. There's no such thing. Throw it out of the window right now before I even stop the video. There is no quotient rule in integration. No way. There's no way. Quotient rule is for differentiation, when you are differentiating things that are dividing. So don't ever think of quotient rule in integration. There is no such thing. Then chain rule now is going to be, the chain rule is now the last one, which is going to be when you have what? You ask me, what is the chain rule? Chain rule is deep. Chain rule is deep. Chain rule is just when you have a function inside another. If I say, for example, you have y is equal to ln of, let's just start with an easy one, ln of 3x. Now, which function is this? Don't you dare say this is a logarithmic function. You'll be correct and wrong. Because our logarithmic function is y equal to ln x. That's the logarithmic one. This is not an x. This is something which is not x. So it is y equal to ln of something which is not x. That's chain rule. Because chain rule, that's a composite function. And to differentiate it, you need the chain rule. Okay? So it's not chain rule. Chain rule is a method we use to differentiate. This type of function is called a composite function, where you put a function inside another. So you have put 3x, which is a what? A polynomial or an algebraic function. You have put it inside of your logarithmic function. That makes it this is making it a composite function, a function of a function. We could have said y is ln of sine x. It's the same thing. Or to say y is equal to ln of, let's say what? Ln of what? Make it nicer. Ln of x cubed minus 2x, whatever. This is, you see, you can even say y is equal to cos of 5x squared minus 9 or whatever. This is another chain rule. You know, because we know that the cos was supposed to be cos x. If we see it being cos of something which is not x, because cos x is the trig one. If you see it being something which is not x, that's now a composite function, and that is where we use the chain rule. So chain rule is very easy to see actually. Even if I say cos 3x is a composite function, people. It is. You have to use the chain rule when you're differentiating him, because it's cos of something which is not an x. You understand? So you're putting something inside town. You can even have, for polynomials, for them to be called composite. It's like if I say x cubed plus 7x and I say to the power of 5. This is not, don't you say this is an algebraic. No, the algebraic is this guy inside. But look, he's raised to another power outside. Now that makes it composite. You see, they could even have said y is equal to the square root of 2x minus 9. This is a composite function. You may say to me, no. I saw you put square root cantile and you did not call that a composite function. I'll say, ma'am, I put square root on one thing. This will change to be x to the power half. But when you have square root on the whole thing, that's now y is equal to 2x minus 9 all to the power half. That's now a composite function, fam. And that makes you need the chain rule. So everybody has seen. What have you seen? Ask me what I've been teaching you. Ask. Okay, let me tell you what I've been teaching you. So I've been teaching you what the word product rule, quotient rule, chain rule, where they now come in. Because you're trying to have a picture of this whole differentiation, integration stuff. So I'm saying, first of all, we learned the types of functions, and we need to know how to differentiate them. And this is easy because we are just given a table, and we can remember it, where we know what the derivative of each one of them is. So that one is not going to be easy. It's not going to be hard, rather. But now we said it doesn't end there, because you say to me, okay, the table I can know. Where does the quotient rule and these other things come in? They just come in when you are now combining them. Although there's this other rule which you may see or you may know about called the power rule. Power rule is not really a rule. It's not really things that you're combining. It just tells you how to differentiate an algebraic thing. 3x squared minus 5x plus 9. Because for algebraic, you won't see them in the table. These ones, we know how to do it because we know the power rule. The power rule says if you have something, if y is equal to ax to the n, then dy dx, for you to get the derivative, you drop down the power. So the power is n, you drop it down. It will multiply a. And then you reduce the power by 1. It is x now to the n minus 1. So the product rule just says when you're differentiating an algebraic thing or a polynomial, that's the easiest thing to differentiate. It says drop the power and reduce it by 1. So here y will be 2 times 3, 6. Then it is x to the 1. Then here, if something is an x, it just reduces to minus 5. Then the derivative of a constant is nothing. So this is the power rule which we've been using. You understand? That's just the rule. So anyway, differentiation, you are set. Okay? One last thing which you would need to know in differentiation is how you differentiate implicit and parametric functions. Those are just type of equations, and I'll show you. I mean, you can remember them by heart. Implicit and parametric. Those are the last ones where we'll be saying, my friend, an implicit equation, you need to know differentiation of implicit. An implicit equation is one where you cannot make y the subject. So it's like you'll be having x squared y plus xy squared minus 3y cubed or minus 3, I don't know, whatever, is equal to 0 or what. Then we say, please differentiate this. Don't ever think you can make y the subject here. It is impossible to make y the subject. So you are just going to have to differentiate it like this. You know, we are used to explicit where you actually have y is equal to something. That's called an explicit equation, and you just get your dy dx. But for this one, you actually have to differentiate it in this format, and you will just be teaching you. So for implicit is when you're differentiating something like this, okay? Then you need to know how to differentiate parametric equations. So you need to know how to differentiate implicit equations and parametric equations. The parametric equations will be just what? Parametric equations will be saying this is when you have two different equations representing the same function, okay? And they'll be in a variable, like to say x is equal to 5t minus 3, and then we say y is equal to 2t squared minus 6t plus 8. So you have x and you have y. Now you'll be actually wanting dy dx. That's the one you want. But you have an x in form of t and you have y in the form of t. So that means here you can actually get dx dt and you can actually get only dy dt within this one, because y is in terms of t and x is in terms of t. So now you'll be just combining those two to then get dy dx by saying it will be dy dt times what? Times dx dt. Now, no, times dt dx rather. Times dt dx. That's how you're going to get your dy dx, okay? It's like the dt's will cancel, although they can't. But it's like they'll do that. So you say to me now, what? I don't have dt dx. I have dx dt. I'll say yes. This is just the same as saying now dy dt times 1 over dx dt, because you want dt dx, which is just 1 over dx dt. So whatever answer you'd have gotten for dx dt, you say 1 over, then you multiply it by the answer you get for dy dt, and you're going to have your dy dx. That is parametric. Look how easy it is. For implicit, you'll be just knowing that whenever you differentiate a y, you should put dy dx after that, and you'll be actually treating these two as x squared and y as product, because you have an x squared multiplying a y and they are two different functions. So you actually then use the product rule. You actually need to know the product rule, by the way. I've just shown you where you use it when two things are multiplying and you're asked to differentiate, but you must then go and know what it actually says. The quotient rule is when things are dividing. The chain rule is when you have composite functions, and then you have implicit and parametric. We'll say you are done with differentiation. You know all the differentiation concepts. If you're done like that, you rest. We'll say rest easy, brother. You are good now, okay? You are, sorry, not rest easy. Rest easy. I don't know what it means. Anyway, that's what it is. You see? Now let's talk about integration. I know you are getting better. What I want you to know is that I can look at a problem and know what method to use by looking at it, because I've studied the cases, and that's what I'm making you know. Don't ever go on the ride that says, no, you can't know an integration concept by looking at the question. You can. You definitely can. I've showed you how you can see the product rule, situation, and all this. Now, let's go through now the integration, guys. And for integration, we don't have product rule. Our product rule is you'll be having these methods now, by parts and whatever, which we are using when you are going to be combining the functions in different ways. You understand? Good. That is where so integration has no product rule. There is no product rule. Product rule is for differentiation. Integration has by parts, by partial fractions. Those are the same words as what you were saying, product rule in differentiation. So in here you'll be now combining, but you're going to say, oh, for this one I use U sub. Oh, for this one I use by parts. Just like in differentiation you were saying, for this one I use product rule. For this one I use chain rule. Are you hearing? Good. Now let's go and let's see the situations. And you see, with practice and with you're going to get better, and you're going to get really, really good. Now, I just hope you're going to recommend this video to your friends. Make sure everybody watches this, okay? That is if I put it on a public domain. But that is it. Team Clarify. Goodbye. Let's meet in the next one.